What if a decision you make right now could influence something that has already happened? This idea sounds impossible, but a real physics experiment suggests something very close to it. Welcome to the first episode of the Unreal Experiment series. To understand this, imagine a simple setup. Scientists fire tiny particles of light called photons toward a wall with two narrow slits. Behind the slits is a screen that records where each particle lands. If light were just made of particles, you would expect each photon to go through one slit or the other, creating two clear lines on the screen. But that's not what happens. Instead, the screen shows a pattern of multiple bright and dark bands, similar to ripples overlapping in water. This pattern is called an interference pattern, and it only appears when something behaves like a wave. So light, which we expect to act like particles, is behaving like a wave. It gets more surprising. Even when scientists send one photon at a time, the interference pattern still forms gradually. Each photon seems to contribute to a larger wave pattern, as if it somehow passed through both slits at once and interfered with itself. This suggests that before being measured, each photon doesn't take a single path. It exists in multiple possible paths at the same time. Now, scientists add a detector near the slits to observe which path the photon actually takes. The moment they do this, the interference pattern disappears. Instead of many bands, the screen now shows two simple lines, exactly what you would expect from particles. So the act of measuring which slit the photon goes through forces it to behave like a particle instead of a wave. At this point, it seems like observation affects the outcome. But the next step is what makes this experiment extraordinary. Instead of deciding whether to measure the photon before it reaches the slits, scientists delay the decision. The photon passes through the slits first. Only after it has already gone through do they choose whether to measure its path or not. If they choose to measure it, the result shows particle-like behavior as if the photon went through only one slit. If they choose not to measure it, the result shows wave-like behavior as if the photon went through both slits. The key point is this: the choice is made after the photon has already passed the slits, yet the outcome still matches that later decision. This experiment is known as the delayed choice experiment. It does not mean that we are literally changing the past. Instead, it reveals something deeper about how reality works at the quantum level. In quantum physics, particles are not fixed objects with definite properties before measurement. They exist in a range of possibilities, often described as a superposition. Only when a measurement is made does one of those possibilities become the observed outcome. The delayed choice experiment shows that what we consider the past behavior of a particle is not fully determined until the measurement happens. In other words, the photon does not commit to being a wave or a particle until the experiment forces a result. This challenges the idea that events have definite outcomes independent of observation. It suggests that at a fundamental level, reality is not a fixed sequence of events, but something that becomes definite only when interactions occur. This leads to deeper questions. If the behavior of a particle is not decided until it is measured, what does that say about cause and effect? Does time always move in a single direction from past to future? Or is the relationship between events more complex than it appears? And if observation plays such a key role, what exactly counts as a measurement? These questions are still being explored, and there is no single agreed answer. What we do know is that experiments like this have been repeated and confirmed, and they consistently show the same results. At the smallest scales, reality does not behave the way our everyday intuition expects. So the next time you think of time as a straight line from past to future, remember this: at the quantum level, the story is not fully written until it is observed. And that raises a final question. If reality depends on observation, then what is time? Follow for the next episode, where the experiments become even more difficult to explain.